Hey there, this is video 8.3. We're looking at slopes of distant time graphs. And basically this is some heavy duty physics, either grade 10 physics or probably the very beginning of, I guess it would be physical sciences 20 now. Anyway, so we saw this before in chapter 6, unit 6, where we did lines, and I talked a little bit slope. Is by definition is rise over run. So it's always the up and down versus the horizontal. And in fact, you can even write it like that, where that little bitty triangle, and I don't think I've used it yet this year, is the symbol delta. Just like that one is sigma, and that one's pi, and there's, whoop, sorry, that's theta, that's sigma, right? It's just another Greek letter, and it's a delta, and it means change. So the change in y or the change in x. Well, y is the up and down axis. X is a horizontal axis. There's a different way of writing it. And speed is distance per time. You know that. It's like so many kilometers per hour. So it's a distance divided by time. So if you look on the graph, your distance, that's the y-axis, and time is your x-axis. So the point is, if you find the slope of a distance time graph, you're finding the speed of the vehicle or whatever's moving. All right, so the movement of a toy car is shown in the graph. Determine the speed of the car during each of the segments. So a little bit closer with the camera. Right, so easiest way to do it, you can do it a bunch of ways. I'm a fan of triangles. So all you do, so here's the beginning of A, here's the end of A, and I'm just going to connect those with a nice right triangle. Oh, and I forgot one thing, slope. Symbol for slope is M. So let's do it this way. So for part A, M is equal to rise over run. Now, how many did it go up? All you do is count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I guess you could have just looked and saw it done. Either one's fine. Over the run of 1, 2, 3, 4, 5, right? Between 4 and 6, that's got to be 5. So M is equal to 2. Now, specifically, because this is a distance time graph, to what? Well, what was the 10? The 10 was in meters, and this was in seconds, so this is in meters per second. And ta-da, there we go. I should show you, because I tend to forget to do this. If I pick that point, and I pick that point, I'm still looking at distance number A. And let's say instead of picking the 2 points at the end, I pick these points kind of in the middle. Where am I going to do it? Put it out here. M is equal to rise. Sorry about the shadows today. Overrun. Okay, it goes 1, 2, 3, 4 up. Over a run of 2. And that's going to be meters per second also. So what's the point? Is anywhere you take the slope on that line, if it's a nice, it has to be a straight line, obviously, but wherever you take the slope, you're always going to get the same answer. Generally, this is just something I've done forever. I try and take the points far apart. Have it. That's all I got for you. All right, let's do the next part. Let's go B. And M is equal to rise over run. My slope. All right, well, I'll use a pen this time. So we went up 1, 2, 3, 4, 5, 6, 7, 8 boxes. And we went across 1, 2, 3. But wait, what did I miss? Do you remember from slope? Yeah, you're always reading your graph from left to right. So this one actually didn't go up 8, it went down 8. So as you're reading left to right, if it goes downhill, then that's a negative slope. So M is equal to negative 8 over 3. Most of the time you can leave slopes as fractions, but right, we can do M is equal to negative 2.7. Take a look at C. C causes some grief. Still got our same formula. I'm not starting with anything else. But if we put a dot at the beginning of the line C and at the end of C, how much did it go up or down? Yeah, it didn't. So M is equal to 0 over 1, 2, 3, 4, 5. It really doesn't matter. 5. And if we think of it in terms of 0 meters per second, what's the object doing? Nothing. It's stopped. So remember that when it's flat like that, when it's a straight horizontal line, that means no movement. Let's go back for a minute. What does this mean? Okay, so 2 meters per second. So this is our start, and away it went. What does a negative mean? Well, it returned towards the start. So this is going away from the start. The negative is going, away from the start. This is returning towards our start. And now what I would like you to do, I bet you can pause the video and do part D all by yourself. How about you do that? Okay, I'm going to trust you did that. So, whoops, it's not D is equal to rise over run. This is part D. So M. So I better draw my triangle. Oh, a minute. Yeah, nope. You could, if you want, draw the triangle on the other side. You could definitely draw it here. I don't know why, but that just weirds me out. I don't want to do that. I like doing my rise over run in this direction. All right, so this is part D. And we went up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Over a run of 2. So M is equal to 5 meters per second. Again, your units, this was 10 meters, so the vertical is meters. That's second, so it's meters per second. Now, this all made sense, and then it got weird. What is happening to the car during segment E? Well, here comes the physics for you. If you have a straight line, that represents uniform motion. This is representing non-uniform motion, which basically means it's either speeding up or slowing down. So there's some kind of acceleration or deceleration going on. Oops. And how do you tell the difference? Well, don't know if that moves for you, but I can't see what I'm doing. What you do is you take your ruler, and if we kind of start at the very beginning, and I just drew what's called a tangent line, so it's kind of along, kind of along that line. And now if I take a look at, say, this point, and then kind of at the very end, can you see what's happening to the slopes of the line? This first one was really steep, and then it became less steep, and then it became less steep. So what do you call it when your speed slows down? Exactly, you're decelerating. And I'd be completely cool with that answer. Decelerating, I'm pretty sure that's how you spell it. Basically, excuse me, you're putting on the brakes. Okay, but a curve is equal to a change in velocity or change in speed. Whereas a straight line is a constant speed. All right, what generalizations can you make about the slope of the line and the speed of the car? Well, let's look at this one. So if we look at A and we look at D, so D is definitely a steeper slope. And then if you look at the actual speeds, A is 2 meters per second and D is 5 meters per second. So the steeper the slope, the faster the car. The faster the speed. And we can also say a negative slope means you're returning to the origin or wherever your starting point was. All right, let's look at this last one. It took me a while to find a graph like this. Explain the motion from the start to the end. No number is required. Okay, so let's just kind of orally go through it. So we're going at a pretty fast speed here. Slow down here. That one to me looks like, to me it looks flat. So that means they stopped and then they went pretty fast. I don't know if it's as fast that one, pretty fast. And then, what's this one? Okay, so I'm going to call this part A and part B and part C and part D. Okay, so A, that's got a negative slope. So returning to origin, can't talk. Instead of origin, I'm just going to say start. Okay, but then, so they go all the way to the start, and then they actually go further. So B is keep going in the same direction. And went past start. Whoops. C, you know what happened. They stopped. And D, returns back to start. And I think I'm just going to leave it there. I really wish that we were together in a classroom because we could act this out. So I guess I'll kind of do it orally and you can imagine, if you will. All right, so this is me. I'm standing at the door and I'm walking away from the door kind of pretty fast, and then I slow down and then I stop and then I go really fast away from the door and then I go turn around and I go back towards the door, there's the door, and then I go through the door and I'm walking around in the hallway and then I stop and go, oh, I missed the door. And then I come back and I end up back at the door. So much cooler when you guys see that live and in person. And I hope we're able to do that.